Ladies and gentlemen, I'm going to dissect a binary tree. Now, what that basically means is I'm going to show you the code, I'm going to visualize how it works. Please keep in mind that this is using composition in object-oriented programming. There are different ways we can build a binary tree using different methods. This is one which the Cambridge examination board like to use in their pseudocode, so why not just use the same in our program code? You may find that you can build it more efficiently. The way I'm doing it is to make it easier to understand, and also this is the iterative version of it rather than using recursion. So to begin with, what I've done is I've created a class. This class is called the leaf, i.e. the node. It will look like this. If I was to draw it out, it would have a left and it would have a right hand side. So our left would be for our left pointer, our right will be for our right pointer, and this will be my data. Every time we create a new leaf, the data and mine would say empty inside of it, just for visuals. Thank you to one of my students for giving me that as an idea for a nice visual, Brandon. Every time we create a leaf, we would also need to give it a value for left and right. So it would have a value in there, and then have a value in there. So every time we make a leaf, it would have 3 different values, an X, a Y, and the data itself. Now the data itself is already going to be in there by default as empty. Keep that in mind. The left and right is going to be passed in when we build our tree, because what we want to do is build a tree which will look kind of like this in different. So this is a leaf. And this imagine we built one with 5 different leaves in it. This is another leaf. This is another leaf. This is another leaf. Let's just do 4, in fact. The leaf is split into 3 sections, where it's empty, 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 and empty. And what we want to do is we want to code it so that this will be always -1. Now I could actually just simply put in -1 here and only pass in the left, because this is always going to be -1 no matter what. In fact, that would have been better for me to do. And then what we want is the left one to go up by 1 each time, because if this is position 0, this is position 1, this is position 2, and this is position 3, we want this to point to 1, we want this to point to the second one, which is here, we want this one to point to the final one, and we want this to be equal to -1. So we have to pass in a different value each time. This is different to this, which is different to this, which is different to this. Therefore, this is a parameter, because we're changing it each time we make a new leaf. So what does that look like from the actual data structure itself? Well, what we're going to be creating is a list of binary tree. So it'll look like this, where all the right nodes will point to -1 when it's empty. And obviously, as I said before, these point to the next one. So this is 0, 1, 2, 3. And inside of here will be E for empty. This code here just sets up, I didn't mean to do that. It just sets up the actual leaf itself. And we're going to repeat this setting up of this leaf, in my example, 10 times. So let's have a look at the code for this. This is my second class. So we've got 2 different classes, one for leaf, one for binary tree. So if I was to do a class diagram, we've got one for leaf, and we've got another, which is called my binary tree. My leaf has got these attributes. My binary tree has these attributes. So let's coach you through this very, very quickly. So if I was to, let me just make this a bit smaller so I can actually annotate on this a bit better. Set up this tree here. It would look something like this. I've given an attribute called self.root, and that's going to be pointing to -1. We've got another attribute called self.free. That's going to be pointing to 0. I'm then going to create an array. So let's build my array right now. And it's going to go 10 times. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's just make this a bit bigger. Okay, so I've got my array. Oh my gosh, did not mean to do that. Please just delete the line. That is so annoying. Whatever, we'll leave the line there. Okay. This is now using the class leaf. So we've got a relationship here between this class and class binary tree. There's a link. The link is this leaf. What we're going to do is we're going to use this template 10 times as well. So watch what happens. It's going to put in 1 leaf. We're going to put in our left pointer, which will be I. I will start on 0, but it's going to be 0 plus 1. So actually our left is going to be 1. Inside our right pointer, it's going to pass in -1. And it's not going to put anything in the data. The data is going to still be empty like we built earlier, where we built our leaf node, where I showed you that. And it's going to do this 10 times. And each time we put in a new leaf into this list, it takes the left side and it makes I plus 1. So I was 0 before, now it's going to be 1, but plus 1 equals 2. -1, empty. And it's going to repeat this process until we get to the end. So let's imagine that we're now at the end. What it's going to do is it's going to still do the same. It's going to do I plus 1, so it's going to be 10. It's going to be empty. And it's going to be -1. So this is a free list. There's nothing in there at the moment. Nothing's being used. We've got no data. This code is now saying, okay, let's get the last element, which is this, and set it to be -1 instead, because it's pointing to nothing, as this is the last element in the binary tree. Nice and simple. Okay. As we've got nothing in our tree, the root pointer is going to be pointing to -1. The moment we put data inside our tree, let's say like USA. That's a really bad count to use, USA. Our root pointer is now going to point to 0. And our free pointer is going to point to the next available space we've got, which is 1. That is what we're going to do in a bit. But just so that we're understanding, what we're creating right now is an empty binary tree of 10 different items in a list, all of them empty. The left-hand side goes up by 1 each time. The right-hand side stays at null. And that is what we're creating here. This relationship between leaf and this class leaf, so the binary tree and this, is using composition, which is a feature of object-oriented programming. Okay. What I've done then is created a new method inside binary tree called add. It's responsible for adding or inserting a new value into a binary tree. I've made this class really tiny because we're not using it anymore. We only used it to build the tree. What we do care about, obviously, are this class's attributes, but we don't really need to talk about class leaf anymore. Okay, so let's imagine we've got our binary tree and let's draw it out like a tree. And I'm only going to do it for like 3 nodes or 3 leaves. Empty. I'm going to just do E for empty. position 0, position 1, position 2. Right pointer is always pointing to -1 when it's empty. This is pointing to 1, this is pointing to 2, and this is also pointing to -1 because it's not pointing to anything else. I want to add USA. So I need to start off by checking the root. But before I want to check the root, I actually want to see whether or not our free list is pointing to -1. So we've got a free list pointer, which points to the next available space. So at the moment, it'll be pointing to here because that's the next available space. So if we put USA, we put it into the free pointer position, which is here. But let's imagine that we had something in here. So I'm going to do yellow. We've got something in there. We've got USA, let's say France, let's say Germany. And we want to put in Italy. The free pointer will be pointing to this. We want to put in Italy. The problem with this, in fact, this should say greater than, but never mind, we can fix that in a minute. The problem with this is that there's no more room in the in. There's no more nodes left. We're full up. So this bit of code is basically saying if self.free is the length of self.tree, print full, return false. So anytime I add a new item, it checks to see whether or not our free pointer is at its maximum. Because if it's at its maximum, there's no more room for it to add anything more. So it's going to say false and then quit this function. So if I try to add Italy and free pointer is at the moment here, it's going to say no more room. But I actually should be saying if it's greater than, because what I'm going to do is every time we add something, so let's imagine that we add something here and the free pointer was here, I'm going to make it go up by 1. That'll make sense later on, but the point being is this code here is checking to see if there's any more room left in our list. If we've got a list and our free pointer is pointing to the next available space, and we've got like Italy, USA, and Germany, and the free pointer is pointing to here, there's no more room left because there's no more available space. So we can't add Russia to it, for example. Whoops. Okay. So the next bit, what we're checking is our self.root equal to -1? Well, think about it like this. We've got a brand new binary tree. We want to enter in USA. Is there any point in us having to check to see where USA is in our binary tree if there's nothing in the root pointer? Remember, the root pointer is pointing to the beginning of our tree, the first node. So we could have like USA, and then we could have like England. So the root will always be pointing to the first node. But if there's no first node, or no data in the first node, should I say, what am I going to do with USA? We know for a fact it's going to be put in here. We don't need to go searching for where it needs to live. So straight away I'm saying, if root is -1, that means it's pointing to nothing, null. There's nothing in our tree, because that's what would happen. If there's nothing in our binary tree, root will be pointing to nothing at the moment. I'm going to put in the value USA in position 0, which is this. This is position 0, position 1, 2, 3, 4. I'm then going to make the root pointing to 0, so it's pointing now to USA. I'm now going to make the free list pointer pointing to position 1, that's the next available space. I'm now going to set the left and right of this to be -1, -1, and all of these are going to be empty. don't forget that this is always going to be -1, -1, -1, -1, and this is going to be pointing to position 2, position 3, position 4, and -1. Let me just tidy this up slightly. So we've just entered in USA. Really, we don't need to do this self.right equals -1 either. So we can make this a little bit more efficient because it already has -1 when we built the leaf to begin with. Okay. Nice and simple so far, I'm hoping. So right now, we've added anything into our root. This could also be if self.3 equals 0. It's the same thing. We're basically saying if the 3 pointer is pointed there, we need to put something into our root node. So we've got an understanding of this. We've got an understanding of this now. Remember, this was to deal with the root and the 3 pointer. What we're going to do now, though, is deal with adding data like another country into this binary tree and working out where we're meant to put it. This piece of code is only focusing on the right-hand side at the moment. Now, if you remember with a binary tree, anything which is larger than goes to the right, anything which is smaller than goes to the left. So I'm going to change the country to put in, let's put in France as our starting country. Let's imagine that the data I enter, the value, is going to be Germany. I want it to compare it with France. Now remember that this is the root pointer, but it's pointing to nothing at the moment because there's nothing else in our in our binary tree. Whereas this is our free list. We've got 2 more nodes left in this example. So I can put Germany in because I've got 2 more spaces left. The free list is pointing to here. I want it to compare G for Germany with France. Is Germany bigger than France? Yes. So what I want to happen is the following. I want to basically take this node. So I'm just going to take it. We're going to put it into our tree. And we're going to put it to the right hand side because F is smaller than G, Germany. How does that change things? Well, it doesn't change our left pointer because it's pointing to nothing still. But our right pointer is now pointing to position 1. So I'm going to put 1 in here because we're pointing to 1. This is 1. Now Germany is pointing to nothing. This 3 pointer is pointing to number 2. There's nothing there. It's not pointing to anything. We've got 1 more node left. Now let's imagine our next one is Holland. I want it to check against France. Is Holland bigger than France? Yes. Is Holland bigger than Germany? Yes. So what do I want to happen? I want it to basically, whoa, that's cool. I didn't realize I can do a straight line. Put in Holland here. So we're basically using this node. This is going to be -1. This is -1 because it's not pointing to anything. Germany is now pointing to 2 on the right hand side. So this should be our final linked, sorry, well, I keep saying linked list, but binary tree. The reason why I keep saying linked list is it's very similar to a linked list. Okay, so we've got, and if I draw our list out, we've got France, we've got Germany, and we've got Holland. France is pointed to nothing on the left hand side, but Germany on the right hand side, so 0, 1. Whoa, okay, didn't mean to do that, so let's zoom out. 1, 2. Germany is pointing to Holland on the right hand side because H is bigger than G, but nothing to the left, and -1, -1. That is what we're hoping to do. I'm going to coach you through the code I've done for this. So let's rock and roll. I'm just going to undo all of this. And let's draw out our table, our list. So let's imagine that we've got France in our root. I'm just going to move this toolbar somewhere so it doesn't bother me, or can I just zoom out? There you go. Okay. So we've got France. We've got our 3-pointer. And we've got our root pointer. The 3-pointer is pointing to 1. Root pointer is pointing to 0. -1, -1. Position 0, position 1, position 2, position 3, position 4. Okay. This code is going to keep repeating itself until we find the next available space to put in Germany. Keep in mind it's Germany. What I'm going to do is I'm going to check to see if Germany is bigger than something called cur. Now you notice I've got something called cur here. It's a variable. It's not an attribute, it's just a normal variable. I'm using it for a reason. So I'm going to put it here. And cur is going to start on 0. That's going to be like a current position. And this will make sense in a second. So is value, which is G for Germany, bigger than self.tree, 0 for cur, dot data, i.e. France. So is it bigger than that? Yes or no? Well, Germany is bigger than France. So the next thing we want to check to see is if self.tree cur, which is 0, dot right, so we're looking at this pointer, is not equal to -1. Well, it is equal to -1. Because it's equal to -1, it means that we know that this is the end of our binary tree on the right-hand side. If we had France, it's pointing to nothing. It's empty. So, because it is -1, we're going to run this if state, this else. The first thing we're going to do is we're going to go self.tree, cur, which is 0, dot right, which is -1, and allocate it for position of self.3. So self.3, the 3-pointer, is pointing to here. This is the next available space. So look what I'm going to do. It basically changes this to point to 1. Why? Because that is where we're going to put Germany. Self.3, which is 1, is where Germany is going to go. And we're going to put it on the right-hand side because it's bigger than France. We're then going to make Germany's left pointer -1 and its right pointer -1. We're then going to increment self.3. Let's imagine now we put in Holland. So cur is 0. It's going to check if Holland is bigger than self.tree, 0 data. So is Holland bigger than France? Yes, it is. Great. Let's check the right-hand side of 0. Is it -1? No, it's not. Okay, so if it's not, let's do the else. Okay, so let's do self.tree. Sorry, I'm an idiot. Let me go back a step. So I'm pretty tired now. So if self.tree cur is not equal to -1, well, it's not equal to -1, so it will run this if statement. So this line is going to run. And what we're going to do is we're going to put into cur self.tree 0 for right pointer, which is 1. So now cur is 1. I'm going to show you why in a second. It then loops again, because we're not going to do this else, it just loops again. If value, which is Holland, is bigger than self.tree cur, which is now 1, so we're comparing it to Germany. Is H bigger than G? Yes, it is. If self.tree cur, which is 1, dot right is not equal to -1, well, it is -1, so we now do the else. So self.tree cur, which is 1, dot right, which is this. We change it to be self.free, which is a free pointer. Why? Because that is where we're going to be pointing to next. Germany will point to Holland. We put Holland in because of this bit. We then do the left -1, the right -1, and the free pointer becoming number 3. Let's do one more, and then I'm going to show you the different visual. Cur starts back at 0 again. Let's imagine that we do Russia. So, let's do this a little bit more quicker. Russia is bigger than France, we know that. It checks to see the right pointer of 0, cur being 0, it's not -1, it's 1. So we loop again. Russia, but sorry, before we loop again, we need to make sure that cur is the right pointer, which is going to be now 1. So we loop again. We're now checking Russia against Germany. Russia is bigger than Germany. If Germany's right pointer is -1, well, it's not -1, it's 2. So what we're going to do, we're going to get cur, and we're going to give it self.tree cur right. So cur is now going to be number 2, i.e. Holland. We now check Russia against Holland. We check the right pointer of Holland is -1, so we now know that Russia will go in here. It updates this to point to 3. This -1, -1, and the free pointer goes up to 4. So, this is relatively simple-ish so far. I'm now going to show you all of this with the left as well. The left code is exactly the same as the right code, apart from we're going to have an elif instead of this if, and I'm going to do it down here. What you'll notice is that the left hand side, which is basically this, is exactly the same as the right hand side, apart from I switched the greater than and less than sign around, so I switched these two signs around. And we're focusing on the left pointer, not the right pointer. Okay, so let's draw this out in a slightly different way, the tree version. So let's do France. -1, -1. We want to add Germany. We've got our free pointer, we've got our root pointer, and we've got our cur. Free pointer, so root pointer is pointing to 0, free pointer will now be pointing to 1. Germany against France. We know that if we run the code, it's going to be this bit which runs, because Germany is bigger than France. We know that it's -1. So we know that cur is -1, because cur is 0, we check the right pointer, it's -1. And what we're going to do is, therefore, we're going to put in Germany. We're going to update cur's right pointer to be the free pointer, which is this bit here. So we're going to put free pointer into here. So it's going to be 1, not -1. And we're going to put -1, -1 here for Germany. Let's do, again, Holland. So it checks it against this. We know that it's, so we look at cur. It's bigger than France. H is bigger than France. If we then look at the right pointer, it's not equal to -1. So what do? We make cur equal the right pointer, which is 1. We loop again. We check to see now Germany against Holland. That's what this is doing. Is K equal to -1? It is equal to -1, so we don't do this if we do the else statement, where we put in Holland we make sure that the current K right pointer is pointing to the 3 pointer, which it would have been 2, it should have gone up, and -1, -1, and the 3 pointer is now going to be number 3, so it's gone up. Every time we add, remember, 3 pointer goes up. So we've now got position 0, position 1, position 2, our 3 pointers position 3, K goes back to 0 again, and our root pointer is always staying at 0. Let's imagine now that we do England. So, remember K starts at 0. So we're checking if value, which is England, is bigger than France. It's not. So we jump down to here. If value, which is England, is it smaller than France? Remember, K being 0, this is in 0. Yes, it is smaller. We're now saying, does self.tree K, which is France, the left side equal -1? Yes, it does. So we don't do this if, we do the else, where we're going to put a node. We're then going to put inside of this England. We're going to put -1 on this side, -1 on that side. That's what all of this does for -1. We make the 3 pointer go up by 1. But before we do, look at this line. We're saying self.tree K, which is 0, so France, set your left pointer to be self.3, which is position 3. So now you've got the left side pointing to here and the right side pointing to here. Interesting. Let's now add Croatia. No, let's not do Croatia. Let's do EF. Finland. That says Finland. Cool. So, K, so 3 pointer, remember, is now going to be pointing to 4. K, back to 0 again. So, Finland against France, big or smaller? Smaller. So we're now doing, so it's just done. It's smaller than there, it's not -1, so K is now going to become 3. It loops again. Finland against England. Well, Finland is bigger than England, so we now do this part. So, if self.tree K, which is 3, does the right pointer point to -1? Yes, it does. So we know that Finland, which is bigger than England, left pointer will be -1, right pointer will be -1, and England's right pointer will be self.3, which is 4. To make this link, by doing that, we've got this link here. And this process just goes on and on and on until it is full. It doesn't matter if you follow this algorithm, it works perfectly.